In our last episode, we gave our LLM a sense of time using positional encodings, and we implemented our very first causal self-attention mechanism. Our tokens can finally talk to each other, share context, and obey the laws of time without looking into the future. But if we stop here with just a single self-attention layer, our language model suffers from a massive bottleneck. A single attention mechanism forces the model to calculate one single set of attention weights per token. Think how limiting that is. In human language, a word almost never relates to its sentence in just one way. Take the word "it" in the sentence, "The girl threw the ball because it was heavy." To understand this sentence deeply, the word "it" needs to attend to two completely different things at the same time. The grammatical reference, that is, what is it, which should attend to ball, and the state, that is, what property does it have, which should attend to heavy. If we only have one attention head, the model is forced to average these relationships together into a single vector. It's like trying to force a camera to focus on the background and foreground simultaneously, like I'm trying to do right now, where everything just ends up being blurry. To solve this, we need multi-head attention. Instead of looking at the sequence through a single lens, multi-head attention splits our attention mechanism into several parallel heads. Each head gets its own set of query, key, and value weight matrices. This allows different heads to specialize during training. Head 1 might learn to track pronoun references. Head 2 might learn to track adjectives describing nouns. And Head 3 might focus purely on the word directly adjacent to it for local syntax. By giving the model multiple heads, it can attend to information from different representation subspaces at different positions simultaneously. And here's a trick that was introduced in Attention is All You Need. It doesn't cost extra computation. Instead of making the model h times bigger, we take our total embedding dimension, the submodel, say 512, and split it evenly across h heads, that is, 8 heads. Each head operates on a smaller feature dimension. Computing 8 heads of size 64 takes virtually the exact same computational matrix multiplication cost as computing one head of size 512. So we get multi-perspective reasoning entirely for free. Let's walk through the pipeline step by step. We project our input sequence X through linear layers to create Q, K, and V. We reshape K, Q, and V from batch, the sequence length, and the model into batch, number of heads, the sequence length, and the head dimension. Each of the H heads independently runs causal self-attention in parallel using its own slice of dimensions. We take the outputs from all H heads and stitch them back together side by side along the feature dimension. Finally, we pass this concatenated tensor through a final layer, WO. This layer acts like a synthesizer. It mixes the insights collected by all the individual heads back into a single unified vector representation. Mathematically, the whole operation looks like this. We will implement a complete MultiHeadAttention PyTorch module that includes causal masking. The constructor will be similar to the single head attention. As attributes, it will also have the number of heads and the head dimension. Also, we'll create an output linear layer to combine all the single head attentions. Let's now implement a private method named _split_heads, which will take a tensor of shape batch, the sequence length, the submodel, and reshapes it into batch, the number of heads, the sequence length, and the head dimensions. So each head gets its own slice of features. Finally, in forward, we project the input, split into heads, run scaled causal attention in parallel, concatenate the heads, and mix them with the output WO. Notice how clean this tensor manipulation is. By reshaping Q, K, and V and transposing the dimensions, PyTorch automatically computes attention across all batch items and all heads in parallel on the GPU. Let's write a demo script to see this in action. Save this inside script/demo_multihead.py. Notice that the shape going into multi-head attention is identical to the shape coming out. This is crucial because it means that we can stack multiple attention blocks on top of each other inside a deep transformer architecture. And that is multi-head attention built completely from scratch. As always, the code that we did today is available on a public GitHub repo, link in the description below. And if you have any questions, just comment in the section below. Make sure you hit the subscribe button and like this video, and I'll see you in the next episode. Bye bye.